So again, here is your line, here is your curve. You have y equals x squared. We have the point 1, 4 living out here in the universe. And what we're trying to do is minimize the distance from that point to a point on our curve. So we're trying to find a point on the curve that is the shortest distance away from that point out in the universe. So my equations are y equals x squared, and then the point I have. So what we're going to do is to minimize or find the point on the parabola that is closest, we're going to go back and use our distance formula. So the distance formula is x1 minus x2 squared plus y1 minus y2 squared, which was really just a modified version of Pythagorean theorem. So it's a squared plus b squared, and you take your square root. Where a and b represent the length of the triangle, which we don't know that length, we know the 2 points on it. So this is going to be some unknown point on my triangle. This is going to be the point 1, 4. But that unknown point that is representative of that distance is always going to be represented by the point on the curve x squared. Because whatever the x value is, the y value is going to be that value squared because of the equation y equals x squared. So then when I plug into my distance formula, my x1 is going to be x, my x2 is going to be the point 1, my y1 is going to be x squared, and my y2 is going to be the number 4. So what's nice about that substitution is everything inside that distance formula is in terms of the same variable. So now all I need to do is take my derivative. So you have a couple choices for taking your derivative. If you don't like square roots, you could change it back to d squared, like we have c squared, but then that's kind of like y. So you get 2d dy dx, like you have to have it implicit. Like you have to then move that like back over to the other side, da 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 da. So you just have to like pick which one you want to do. Both are fine. So if I treat it like the derivative of distance, this is a square root, so it's 1/2. And then if you think about it, if you take the derivative of the square root, it becomes the negative square root. So it's 1/2, all that stuff to the negative square root. So all of this is just going to come down in my denominator. So outside is 1/2, all that stuff to the negative 1/2, times the derivative of the inside. So now we just kind of have like chain rules on the inside. So it'd be 2x minus 1 times 1 plus 2 x squared minus 4 times 2x. And then we just clean it up. And you maybe possibly, so I was looking at like these and looking at this, like you could cancel out that 2. So technically all of these are divisible by 2, so you could cancel away that 2. And then at this point I would bust out my calculator because these aren't going to be pretty numbers. Like 2x cubed minus 7x minus 1 is not accurate. So what we would do is take out our graphing calculators, find the zeros, happened to me. Like, there should be a little blackboard sitting back by the, you can grab one of the other ones off that shelf or out of the cupboards over there.
I was trying to turn my old one. I
That,
don't use them that often.
I know. I feel like that's the benefit of like the batteries, that like, my batteries recently have been not lasting. I feel like batteries just got cheaper remade. So you should get 3 zeros. And just, I have all 4 decimals written out on my page, but I already have it written on here. So negative 1.794 negative 0.143, and 1.938. So then what you want to do is if you look at that graph, the graph goes from negative to positive. So if this is negative to positive, and then negative, and then back to positive. If we are trying to find the closest point, that means we're trying to minimize the distance. So we need whichever one of these is going to be a min. And we see that we have two minimums. So if you think about the point negative 1.7 though, that's going to be over here and up there. And then if you think about the point negative or positive 1.93, that's going to be potentially here, and it could be inside, just the way I drew mine. So which point do we think is actually going to be the closest to the point we're looking for? Yeah, the 1.93. The reason you're getting that negative 1.7 number is because of the fact that it's a parabola. And our graph, when we're doing it, is having a hard time determining, are we looking at the positive 1.4 point or the negative? All right. So then we have the top and bottom margins of a poster are each 3 centimeters, and the sides of each are as such. So what that means is we have a poster, and then within the poster we have a printed region. So that should make sense to you because it's like the margins on a paper. So it says the top and bottom margins of a poster are each 3 centimeters. So the distance from here to here is 3 on top and bottom. The sides are 2. If the area of the printed material on the poster is fixed at 192 centimeters cubed squared, so if this is x and this is y, then the area of the printed is x times y is equal to 192. Find the dimensions of the poster with the smallest area. So that represents the printed space. We need to find the dimensions that represent the entire space. So then that means that this outside length is the inside printed length plus both margins. And then the other piece is the inside and both margins again. So the area of the entire poster is x plus 4 times quantity y plus 6. And this is again the case where we're going to use substitution. We're going to substitute out one variable and bring in another. So we know that the area of the printed region is xy equals 192. So we can solve for either x or y and then replace them in the other equation. And then personally, again, you're maximizing or minimizing, so you're deriving, and you have a choice. Do you want to FOIL first or derive with product rule? Personally, I would FOIL, because it's going to let your y's cancel a little bit. Like, I'm only going to have one denominator y instead of 2. But again, there's not a right or a wrong. And then find your derivative. And then find your zeros. And then solve for your y squared, so you get y equals 16.971. I don't care about the negative y squared because, well, like can't be negative. So that gives me my y, that gives me my x. Now, paying attention to what the question asked, it said, find the dimensions of the poster. So I did not find the dimensions of the poster, I found the dimensions of the printed region. The dimensions of the poster need to add 6 and add 4 to both of those numbers. So like you have to take the 11.31 whatever, and then that becomes 15.314, and then we add 6. So my final answer is 22.971 by 15.31. A cylindrical can can hold 1 liter of oil. Find the dimensions that will minimize the cost of metal to manufacture the can. So this one kind of requires a little bit of information. Typically AP will give you that information, but like in a sneaky way. So they might somewhere on this page have that 1 liter is equal to 1,000 cubic centimeters. But like, it may not be as obvious as that, but they're gonna tell you that. So they're not gonna make you need to know what 1 liter is, but they're going to put you in a position where you need to know that you can't use 1 liter in the problem. You need to use centimeters cubed, because we're eventually going to talk about the surface area. And area needs to be in like linear numbers, so centimeters, inches, feet, etc. Where liters is in terms of volume of liquid. So a cylindrical can is made to hold 1 liter of oil. By the dimensions, that will minimize the cost of the metal to manufacture it.
Will the following students please report to the office? Braden Thompson, Kenneth Fuchs, Nathan Patterson, Molly Sheets, Kate Smith, Cecilia Hess, Austin Merck, Doug Seaman, Jacob Stremmel, John Snyder, Tyler Hill,
Really
Nick
short
Gato,
today.
Sierra Bamberger, and Jacob Bamberger.
Do at 9 a.m. They said Furious 1 to 4. Maybe like, there's, I still have a couple more kids that have them. But that was like really fast. 7:45 to 9. An hour and 15 minutes.
X1 squared.
Yeah, I didn't go to that algebra.
I don't know, I did yours too.
Was it? Those have been like a little subdivision.
No, I'm
I'm
not
so
thinking
glad
about
that
I don't know.
I
I'm
remember
not
thinking
thinking about
It's the key, it's the flashcards, it's the flashcards that we went over.
I remember leaving, like, that day that, like, oh yeah, we're not in school for weeks. I just walked in, this entire packet.
Yes.
That just had all this stuff in the flashcards. It's like, do this for whenever you guys come back. Never did it.
I know, I would have went that year, because I was here as Charlotte.
So the surface area of a cylinder, think about a cylinder. You have a circle on top, a circle on bottom, and then if you open up a cylinder, it's really just a rectangle. So two circles. So area of the circle is pi r squared. We have two of them. And then you have a rectangle. So the height of the rectangle or the height of the cylinder is h. And then the length of that rectangle, because again, if you fold it up and make that cylinder, the length of the rectangle is the circumference of the circle. So if you take that rectangle and open it up, or you fold it back into the cylinder, that is the circumference of the circle. So that's how you get surface area of a cylinder if you don't know it. Volume is a little grosser. Volume is area of the two sort of mesh together. So it's actually pi r squared h. Volume is pi r squared h.
So I'm thinking that we'll just have to know.
Sometimes they give you them, sometimes they don't. They usually give you the ones, like they would probably have given you the volume, but not the surface area. Because they would say that you could figure out surface area by knowing what the shape looks like, but you can't figure out the volume. So that's where I think they would be. They give you volume, but not surface area. So what are we trying to minimize? We're trying to minimize the material. So we're minimizing surface area. We're using volume as our formula to get rid of a variable. Because we know the amount of volume the can is holding. So we solve the volume instead of being for V for H. So I can get rid of H in surface area. So what's nice, the pi cancels and r cancels, and it simplifies to 2 pi r squared plus 2,000 over r. I want to do something a little different. If this was a calculator problem, at this point in time, you could use your calculator to do the rest of the problem. So instead of finding the derivative by hand, what I want to do is find the derivative on here with you. So I'm going to show you like a little bit of a cheat method. So what you're going to do is go to y equals, clear out anything you have in y1. And then I want you to take the surface area formula in y1. So So you're gonna take 2 pi r squared, but in this case x squared, plus 2,000 over r. Now, I want you to arrow down to y2. And then in y2, I want you to hit the word math. And then we're going to go all the way down to option number 8, where it says numeric derivative. So what that means is it's going to find the derivative of a number. So it's not going to actually give you the derivative, it's going to find you the derivative at a particular number. So we're going to hit enter, and we're going to put that into our y2. And then what you might notice is it has the d over d. And what are we deriving? Well, we're deriving with respect to x. So we're going to put an x in that bottom. We're taking the derivative of everything in y1. So what you're going to do now is hit bars, go over to y bars, and put y1 inside that function. And then you want to find the derivative at every x. So you're going to put x equals x. So your y2 should look like d over dx, y1, x equals x. Now, what I want you to do is I want you to go to y1 and unhighlight the equal sign. We do not need to graph y1. It's going to slow our calculator down. Okay? Are we ever going to care about a negative x value? So what I like to do too is change my x min to 0. I'm just going to make my x max 10. Because the likelihood that like it's going to have a radius bigger than 10 is pretty slim. So I'm going to graph. What I'm going to do is watch it graph my derivative. Now we could have found the derivative by hand. It wasn't a terrible derivative to find, but this is kind of like a way of using your calculator and not wasting time doing the derivative math. And what you'll notice is it crosses how many times? Once. And if it goes from negative to positive, we're going from decreasing to increasing, so that would be a min. So we're really happy. We hit second trace, go to option number 2, move our little spider on the line to the left, put the spider on the line to the right, and we get that the radius, or the x value, is 5.419 centimeters. We need our height. So that x value is now saved in x. So like, you know, so hit second quick. And you know how like you have like x right here? If you would hit x right now and hit enter, it would have that radius value saved in it. So if you want to find the height, you can do 1,000 divided by pi x squared without having to type in 5.419 and squaring it. You can literally type x squared, because it will plug in that x that you just quote unquote stored. Does that make sense? Everybody okay with that? It's not difficult, it's just that it's like a cool little way to start using your calculator, and this is the unit we really get to use them. So the last little bit of optimization I want to look at has some vocab for it. In the past, I used to make this a couple more days, but I would like to, kind of wrap up optimization today. So I'm giving you the vocab. And then we're going to talk about how that vocab relates. So there is actually an area of calculus called business calc. So if you were going to go and get a business degree, you would actually not take calc, you would take business calc. And you would take a modified version of Calc 1 and 2, focusing on all of the economic and business applications of calculus. And, so it is called like applied calc, and everything in it is ways that calculus is applied. So I always keep my book around because everybody's like, when am I going to use this? How do I use this? Like, calculus is used in econ and for code writing and engineering all the time. They're the only people that will tell you they still use calc because they use it to write their programs. And don't get me wrong, some of their computer systems are smart and kind of run the functions for you, but understanding it is still important. So in calc, we have some vocab. And that vocab allows us to really understand calculus in terms of its use. So we have cost, revenue, and profit. Cost, revenue, and profit are all everyday economic terms. Cost is C, revenue is the number of units sold at the price sold, so we call that X, P of X, and then your profit is your revenue minus your costs. So in calc, we are always looking at averages and derivatives. So the average of any of these is just going to be that value divided by X, because X represents the number of units. Marginal in calculus is the word that means derivative. So I'm not sure I put this like on there because you don't really need it. It's just sort of like, if you hear the word marginal, know that that means derivative. So like the word marginal means derivative. That is literally the only point that you need to get from this slide. So marginal cost, derivative of cost. Marginal revenue, derivative of cost. So what is important and is the first part of your notes is the minimum cost, right? If we're selling something or making something, the goal of the company is to minimize the cost needed to produce it. What does the minimum cost kind of look like? A derivative equal to an average. P-value theorem, yes, because it's f prime of c equals the slope of the secant. Slope of the secant means average of the slopes, right? So the minimum average cost is the economic variation of MBT. If you want to maximize the profit, then you would want P of X equal to R of X minus C of X to be 0 on its derivative, right? So the derivative of profit would be P prime equals R prime X minus C prime X. How do you minimize or maximize something? You find where the derivative is 0. So you would find where the profit's derivative is 0. Well, that would be when R prime of X minus C prime of X equals 0. But that's really just when R prime of X equals C prime of X, because you would just add the other one over. So this is like the shortcut to understanding max profit. So max profit always occurs when the derivative of revenue and the derivative of cost are equal. And really, that's all we would do when we would work our way through a problem. So we have R of x equals 9x, C of x equals all of that. Is there a production level that maximizes profit? So how would you maximize profit? Well, you would do exactly what we just said. Set the derivatives equal to each other. Derivative of R is 9. Derivative of C your x squared minus 12x plus 15. Get the 9 over on the other side. And it is I believe it is not because there are no factors of 2 that will sum you have 2 and 1. So you would find your derivative 0 by quadratic formula or calculator. So you have 2 roots at which this would occur, 0.58 something and 3.4 something. So you would want to look at, okay, which one is a max and which one is a min. So again, looking at that, investigating that. It goes positive, negative, positive. So if we are trying to maximize profit, we are looking for the maximum. So that would be at 2 minus square root of 2. All right, let's skip over the next one because I think you can do MVT pretty well. Derivative equal to blah, blah, blah. I want to look at example 3 because this one's a little bit, it's like another step. So it says you're assigned to design some shipping materials at a minimum cost. So right here, I see minimum and cost. So I know that I am deriving cost to minimize it. The package is a closed box with a square base. So I have a square base and it's a box. So if you think about a box will have 4 sides. Then it also needs to have a lid. It's closed. So one of those sides will have a square attached to it that represents the base or the lid. So base, lid. And then those are all the sides. So it says the package will be a closed rectangular box with a square base and it must have a volume of 50 cubic inches. So we know that volume is length times width times height. So the length and width in this case are both x. The height is an unknown. The material used for the top costs 35 cents. So now we're creating our cost function. So the top material costs 35 cents. So that's 0.35. How would you represent the top's area? What's the area of a square? Yeah, x squared. So the cost would be 0.35 x squared. The material used for the bottom is 45 cents. And the material for the sides is 20. So how many sides does a box have? Yeah, because these are the sides, right? So yes, there are 6 spots, but we already did the top and bottom. So there are technically only 4 sides. And the sides are represented by X and H. So the area of the sides would be X by H. So what's the first problem you notice about the cost function? That's an H. So let's get rid of it using volume. What else do you notice right here? Just because I'm saving myself some space. Those are what? Yeah, let's add them together. You think about 0.2 or 0.8, in the case of this problem, it's like 8 over 10. So we can simplify. The 10 and the 50 to be a 5. 8 times 5 is 40. So I got rid of my decimal, so that makes me happy. And I can get rid of an X. And again, I don't like decimals. I personally would change this 0.8 to 8/10 or 4/5 also. So then C prime of X So then you could multiply. So you have 8x over 5 minus 40 over x squared. So then I got x squared on both sides. I got 5 on both sides. So we know that we can't have a length of 0, so we don't have to worry about the bottom. And then I need 8x cubed to equal 40 times 5 divided by 8. 40 divided by 8 is 5. So I need x cubed to equal 25. And I have no idea what cube root of 25 is, because it's not a perfect cube. No, the cube root of 27 is 3. So my prediction is that it would be a little bit less. So the base you want would be the cube root of 25. And then the height would be 50 divided by 25. Which is approximately like 2.92 something, if that's what makes sense. Makes sense though? This one is probably the closest one.
So, I understand where the particular x is. But where did the numbers for x, like, to just get x?
You want to type it?
After, like, where it says c prime of x, yeah, I got to the 8 cubed times 40 times 5 over 5x squared.
Yeah.
I don't know what that
Oh, I want it here. All right, out. So then since the bottom doesn't matter, because you're gonna get 0,
is. Okay, then you just did something.
I set the top equal to 0. So then when you set the top equal to 0, that 40 times 5 moves to the other side. We'll save the last page for tomorrow, just to give us something to work on. No, worksheet or textbook? Really don't matter.